HPC and AI. Let's also recall Dr. Tomás Lang as brilliant engineer in computer arithmetic and digital architecture. Born in Czechoslovakia, he arrived in Chile in 1939, studied electrical engineering at the University of Chile, and later postgraduate study at Berkeley and Stanford. Our first keynote speaker is Mateo Valero, honoris causa doctor, director of the Barcelona Supercomputing Center, and professor of computer architecture at the Universidad Politécnica de Catalonia. With more than 700 publications and numerous international awards. Professor Valero is a global leader in high-performance computing, whose work has increased Europe's research ecosystem and information technology. Professor Valero, please.
Sí. Buenos días a todos. I don't know if I need to use English, Spanish, or Catalan. You choose Catalan. Bon dia a tothom. It's my pleasure to be here in Chile, third time in 1 year. I think this is the most important, okay, because we are talking about Tomás. Tomás Lang was this guy. Okay? He was always smiling, always thinking. He was unique. When I met him, was in the first lecture he gave in Barcelona. I am telecommunication engineer. I was in the School of Telecommunication Engineer, and he was trying to be hired by the computer science faculty. Okay, so after the first talk we met, and he came to my lab many times, and one day he told me, Mateo, you are not very good using your hands trying to build these circuits. Why you don't try to use your brain? Probably you will be worse, but try to change your mind. And I follow his recommendation, and all the words we heard today here, all the collaboration who were described here is because Tomás was in Barcelona. He started the computer architecture department, and the computer architecture department created the Supercomputing Center. We created the first one 40 years ago. Tomás was arrived in 78. He left in 82, unfortunately. Okay, so, but he left there a seed that grow a lot. I changed my job. So I said, let's go to do things in computer science. At the beginning, we didn't have computers. So we were just using our brain, and so we were doing things as the systolic array processor stuff. I met Jaime. I met all these three guys who were students of Tomás in '86 at UCLA. And then I was expert in connecting the systolic array to a horse. Do you remember the Chinese guy? It was in '86, okay. So we did some work in interconnection network. Tomás was very, very good in interconnection network, but in special in arithmetic, in computer arithmetic with Milos, Erzegovac. Probably he was one of the best in the world. And we start our research. We start creating a group, okay? And then I haven't read ISCA, because ISCA is the best computer conference in our field, International Symposium on Computer Architecture, and I gave the keynote last year or 2 years ago in Buenos Aires. So I was giving more or less the same thing, okay? So I say, I need to change to the field of processor, okay? So I was reading, because I didn't follow any formal course on computer architecture, just one that Tomás gave in Barcelona, okay? But I was reading, and I said, oh, this vector architecture, beautiful, okay? So they were created by Seymour Cray, okay? And then you have some example here. The first supercomputer was 50 years ago, 75, the Cray one. And then what happened, that suddenly the microprocessor appeared, and people believe that the microprocessor will kill the dinosaurs, los dinosaurios, no? So, and then, especially because there were two big projects in the States, the ASCII and the ASCII white and the ASCII red. I don't know, Jaime was working in some of this project, no? You were young at that time, yeah, okay. But listen, they were #1 in the world, 1 teraflops. 1 teraflop is nothing. We have chips now with 100 teraflops, one chip, okay? And it was 97, 73 teraflop in 01. So people thought the vector architecture will disappear. So as I was a young researcher, I said, okay, I will not be famous. Nobody believed in vector architecture, why not me and our people in Barcelona? And then I changed, I started doing research in vector architecture. But at the same time, the microprocessors were increasing the quality, increasing the performance. We were putting more and more things in the design of the Pentium, microprocessor Pentium, okay? So we thought, why don't put together both things? Why we don't use ideas from one field to the other field? And we have some cross-pollination, so we are going to have the best of both worlds in the future microprocessor. The future microprocessors that will be vector architecture, this was our sentence. In the future, in high-performance computing, all the processors will be vector architecture, and this is true today. And we did that. We say that 30 years ago when nobody was doing research in vector architecture because people thought that this architecture were killed forever. So we start that. Here I have the team. But the topics, I will describe some of our topics, some of the things we did, okay? And concerning to the memory access, Tomás was contributing in this topic, in the first one, how to access to the memory, to the elements of the vector out of order. The idea is the Seymour Cray built a machine, everything in order, trying to get the faster clock, the faster technology. It was not disorder, and I am a person that I don't like the order, I like the disorder. So really, ask my wife. So I mean, we were doing things in the access to the memory for one processor and for several processors. And then we introduced this concept we call command because our English still is not good. This is not the right word. So the idea is that the vector architecture, instead of sending element address by address, why the processor send the whole information about the vector to the memory controller. The memory controller will receive all the requests from all the processor and will do the best scheduling, okay? It was very nice, okay? So a few years ago, we used that for the packet switches from Cisco, okay? And so we start with another related field, is just how we better exploit the instruction level parallelization in vector architecture, okay? So we did decoupled vector architecture. The idea of decoupled architecture was from Gene Smith for scalar architecture. We did for vector. Out of order is an idea from the superscalar processor that we apply to the vector architecture, multi-threaded vector architecture, vector microprocessor, short vector, and you have some influence. I remember when we proposed this paper, decoupled vector architecture, in '96, when we met Barton Smith. He said, after reading this paper, we started design of the Cray X1. Okay, he motivated the design of this processor, okay? And we did memory hierarchy organization, okay? Also, we apply things from vector to a scalar processor in the other side, okay? So, for example, you know the MMX were invented by, well, invented because by the Intel, okay, reducing the, if we have 64-bit, we can have 8 by 8 numbers, and we can represent the multimedia, the red, the blue, whatever. Okay, so we apply the vector ideas, and we propose even memory-to-memory vector multimedia architecture. And we also proposed the very instruction word vector architecture, and we realized that a few years later, Intel produced the Myriad processor, who was a very instruction word vector architecture, okay? So we did that, and I like very much this paper in ISCA, where we have a scalar processor, we are executing a scalar code, but the hardware internally recognizes when detecting vector structure in a scalar code and change the mode to convert the scalar to vector architecture. The vector, sorry, means that you are going to execute operation over a set of values, not just individually, so you go faster. I forgot to say that, okay? So this was very important. Another thing we did is that applying, because people thought that the vector architecture will be used only for numerical application, okay? So suppose that you like to do the same operation over different threads, you can have a single control over this thread, and then you know this is one thing that after that is using NVIDIA, okay? If you see the NVIDIA accelerator are vector architecture, simultaneous vector architecture with SYNT and using systolic array processor. All the four ideas that NVIDIA, the main ideas that NVIDIA is using to build their accelerator, this accelerator where the cost is for one chip $30K. And you have to be happy if the Jensen, the guy from, he said, you will get this thing. You had more money, but you're not going to get these chips. The Blackwell is the last one, okay? So we did that for this encryption mechanism using, to encrypt several threads at the same time using vector architecture, okay? Another work we did, I am summarizing, is that following the idea that the vector architecture can be used for another application for the databases. People thought that the vector architecture wouldn't be used for executing databases. This is not true. So we propose new instruction plus new hardware to execute, and we have several patents on this topic, okay? And you have some of the examples here for this field. Okay, changing from vector architecture to scalar architecture, superscalar architecture. So listen, this is a very simple model. I think I took this picture from Gene Smith in one of his papers. Okay, so we have the application. We have the untouchable instruction set architecture. This was very important. And then we had the pipeline. We took the idea to build processor from Henry Ford. The idea from Henry Ford to build the 4T, to establish a pipeline and to have several cars in different states. With the computer architecture, use the same so we do fetch, decode, rename, blah, 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 blah. So we had a very easy work to do during many years. So Mar, Leon, Jaime, Gabi, many people were very happy because we have a simple work to do. Just looking at thread of distraction, the binary, how you change the hardware to go faster, because the idea was to go faster anytime, no? But don't touch the instruction set architecture because you will go to the hell. If you do that, you will go to the hell. So, and that was the worst idea we follow at the computer architecture level, because that delay the work of the parallel processor, the parallel computing. Okay, so we did many works on that. Okay, so we were just looking to get a data flow graph of the algorithm as large as possible to try to detect the maximum parallelism of a single program. So we say the distant parallelism here, and the distant parallelism was very simple. We annotate the programs, and the compiler was able to generate thread, and then these scalar programs were able to be executed in a parallel way, just annotating program. And we say, forbidden, forbidden, kill it. So we say, okay, let's go to doing hardware, because these guys do not like anything related with the software. They are Iron Men, as these three guys who are my friend there, Iron Men. Me too. We just like the hardware, not, well, we like good wine, but okay. So we propose what we call kilo instruction processor, okay, many other things, okay, and I am going to describe the kilo instruction processor and then the virtual register. I am going to describe these two ideas that I think are very, very important. And then, so the distant parallelism is, okay, if you follow the rules that were announced when the people define how superscalar processor works, I mean, depending on the number of instructions you have on fly, you need plenty of hardware. This is not scalable. So for this thing, the processor at that time have 32 instructions on fly. So when the processor found catch miss, it was the end, okay? Until the data from the cache came to the processor was doing nothing, was blocked, okay? So we try, but what would happen if we were able to execute 1,000 instructions, 4,000 instructions in numerical application? If we were able to do that, we would be able to get the maximum performance. And let me tell you, the current microprocessor that in theory can execute 6-8 instructions per cycle, they execute 1.2, 1.3. Okay, they are not very effective. Okay, so we follow this idea, and then we change the way the instruction, the way the processor is designed. Okay, so one of the things we changed was the renaming mechanism. In the renaming, when you do renaming, okay, you do the renaming, and you assign a register to every instruction. But probably this instruction will be executed several cycles later. So all these cycles, this register has been blocked without any use. You just need the dependencies between instructions, okay? So we just, this is the idea of the virtual physical register. So we avoid the use of this register, and we will assign the register when the instruction producing a data for the register is going to be to go to the functional unit. And the same happens with the after a register is produced, when is the last use of the register. And we just propose things just to do the early release. And we propose what we call ephemeral register. I mean, using the minimum number of registers to execute more instruction with the same hardware. So the processor instruction have short latency, long latency, and in order to build a processor, we try to use this locality, and we change the way we build the processor in order to optimize the hardware, okay? One of the things we do is that to do checkpointing out of order commit, and I think that Mar used a little in the ROC processor. When you were in Sun, you announced publicly, thanks once more to you, that you used our papers to build in Sun a very important microprocessor. Okay, so in the superscalar processor, we also propose content aware. Our idea was trying to reduce the hardware, trying to do things totally out of order, trying to get more and more performance. Okay, so we propose many things here, and as I don't have many time, I will comment to you one of the things that I consider very important that we call fuzzy computation. Okay, you know, when you look, this is all. Okay, when you look the the accelerator from NVIDIA or from AMD, you will see that they use different data formats, and this is the base to execute AI applications, okay? If you can do computation under a certain accuracy, use the minimum number of bits, because that will allow you to execute the maximum number of operations per cycle, okay? So now this is the reason why, for example, the Blackwell use FP4, and in the executing inferences in AI application, he can be 30 times faster, because he can use a smaller number of bits and another formats. The E format was not included here because I produced this slide probably 3 years ago, okay? So this is very important to see what kind of data format we use when we have LLMs or we have any of these AI applications. Okay? It's very, very important, because if we can use a few number of bits, we can go very, very fast with the same hardware. Well, so we applied that many, many years ago. We have one of the paper 23 years ago for multimedia. We say, if we change the quality of the pictures, the photographs, and we dynamically change the number of bits for the red, blue, and green, under certain accuracy, we can go faster. And then we did that, we applied that for the reuse. We were reusing the concept reuse. And then we apply that also for floating point numbers. And probably you have here the famous BF16, okay? So I am very proud of this work, because now all the AI, the idea for the title is that there is not, I mean, we can discuss with these guys later, or with all of you, what are the new ideas in computer architecture in the current AI chips? What are the new ideas? I know there are some of them, but the basic ideas are very old ideas. If you complement with this one and the 4 I gave you before, this is the base for the NVIDIA chips. Okay, so we, the bad guys, were destroyed, the scalar guys, okay, and the multi-core appear, and we say, Houston, we have a serious problem. We need to change our world and to be politician, because you can be politician forever, but it's very difficult to be good researcher forever, no? Because you need to change your, okay, sorry. So here what happened is that we have many different multi-cores, and how we pass from the application to this multi-core. So the approach in Barcelona, the Jesus Labart approach, was to give an interface, very clear interface, general purpose single address space, and give the power to the runtime. So you have a simple, clear interface, and depending on the hardware, the runtime will adapt the parallel software to the hardware. It was a very, very, I love this idea from Jesus. He said that he took this idea from the kilo instruction processor, from the distant parallelism, because what he did is annotate the program. You have a scalar program, you annotate, and then the compiler creates these huge data flow graphs, where instead of having instruction, you had processes, you had the dependencies of the processes, and you can do things that we were unable to do in the scalar field, when you have just one thread, and you need to follow, and then we have problem with the branch, we need to wait the branch, because we failed the branch prediction. So, the important thing is that you can change the order of the execution of this graph, and things that were very difficult to do, as the prefetch, the reuse, the eliminating the dependency renaming, were very simple to do in this data flow graph. Jesus is my right hand, so Tomás was my professor. I thought that Jesus is my son, even he's not a very good son. He doesn't like me very much as the real son I have with my wife, so both are not my friends. I am friend of both, but okay. So we did that. So I thought to start another project. This is the last one I started when I was young, 10 years ago. It was the famous ERC in Europe, European Research Council. You can get 3 million, 4 million of euros for an individual to do research. So I propose what we call runtime aware architecture. If we had this runtime and we had different hardware, how we can change the hardware and the software, to allow them to communicate each other in the best way, okay? And then we reuse, there are a few ideas in our field, really. We are not so good producing ideas. So we reuse ideas we were using during many years in the field of the simple single processor, okay? So all the things that we were using in the superscalar world were converted in the multi-core world to this one. The same concept on the left, the same concept on the right, and then we produce many papers, many theses, whatever. So many, the change that Tomás produced in my brain allow my student, because I didn't have any good idea where my student, okay, although I was just trying, giving them good food, good wine, and okay, so we produce many. I think honestly, in vector architecture, we are the best one in the world, giving ideas to the current processor. Also in some superscalar processor. I am going to say anything about the seminal work with in simultaneous multi-thread and very instruction work. Jaime was working a lot in this field, Sistoli, very instruction work, okay, Jaime. And then, I don't know how much time, I have 1 more hour, no? I don't know, no? So this is the quickly, the history of BSC in 5 minutes. So this is, Tomás was on the left, here, okay? He created 82, he left, and we start growing and growing, okay? And then I realized that we should create something to connect with the society here, and I created 40 years ago, the first supercomputing center, research supercomputing center in Barcelona. Was called CEDBA, Centro Europeo de Paralelismo de Barcelona. And then in 2000, thanks to, you have here, let me introduce Jaime Moreno, who is from Chile, and Gaby Silverman. They were 2 people from Chile too. They were 2 people in Watson helping us a lot, and many others. So we create a joint venture with them for 4 years. And this was the origin for the Barcelona Supercomputing Center. Without IBM, the BSC will not exist. And what we did is that we introduced the first commodity supercomputer thanks to the researchers from IBM. Commodity means that at the hardware level, the processor was the PC, the power PC, who were used in the laptop, and for the software, we use the Linux. People advise us, you are going to be killed in 1 month. Neither the hardware nor the software will work. Okay. It was not true. So the BSC was created 20 years ago, and we are the 12th of November. We are celebrating the 20 years anniversary of the BSC. We had plenty of experience in managing small machines. For example, this is the Convex vector architecture, 8 vector. This is the famous connection machine. These were the board we built by us when Tomás met me. I was doing this kind of hardware, yes. Okay, and then until the Mare Nostrum 1 arrived, okay. So this is the Barcelona Supercomputing Center. It's a product of the collaboration between institutions. I convinced 85 to the Spanish government, the Catalan government, and the University of Catalonia to collaborate in this CEDBA. And they have been collaborating for 40 years. Sometimes, you know, with these people who like to be independent in Catalonia, I think the only topic of communication between Barcelona and Madrid was the Barcelona Supercomputing Center and the Sagrada Familia. And now even more, I told to the minister that they had the parliaments have agreements for 10 years. The money we are going to receive every year during 10 years. Now the current one is until 2029. You don't have that, please do not start building supercomputers. This is a serious thing. I say that to the minister. I don't know if I was correct or not. But we had different research. PhD program, I will go quickly. We were created to be 60 people, and we are 1,400 people. Okay, and then 35% from 60 nationalities. You have the distribution of the people. We have a huge computer science department, huge, and then 3 application department. Okay, and then you need to have always people managing, and then people managing the center and managing the computer. We publish, we have 3 application department: engineering, life science, earth science, climate change, personalized medicine, and engineering. I select 20 years ago, I say, Minister, if you like me to be in the Barcelona Supercomputing Center, we need to do a lot of research. I don't like to be a center of service. Okay, and then I select these 2 topics, who are 2 of the main topics today, and you can see the quality of our publication are very good. You can see here the output in the top 10 and the top 1, and the BSc and the Spain, average Spain. So we are very good publishing Nature, Science, all this thing, okay? This is the structure, this is the army. I am not going to describe anything. This is the Department of the Computer Science. I am here, and here the politicians are here. The department I am going to do, the Computer Science Department, we have 4, there is a general and 4 subgeneral: Miquel Moretó, High Performance Computing; Rosa Maria Badia, Software; Ulises Cortés, AI Research, and Embedded Architecture. We have a group of 70 people doing real hardware for hard real time, with patents used by the planes, so good. This is the structure of the Computer Science Department. You will get the slide, okay? And the rest of the department do digital twin, okay? Digital twin. They are happy doing digital twin. Here you have the main digital twin of life science, earth science, and case. This is not important for our topic. Okay, but I am going to the last part. I mean, when you see all the supercomputers in Europe, there is no hardware from Europe. We fully depend on the hardware from the States. So I was predicating as Jesus Christ in the desert in many years. We can do that with the R. Okay, ARM, yes, with the R. The R, A-R-M, is European. Okay, when I received the Seymour Cray Award, I was saying that. And what happened, we built these 2 towers were built by BSc using chips from the latest one from the Samsung Galaxy 4, from the mobile. Every chip has 2 R plus an accelerator, the Mali, and Jesus did the software stack. We were waiting to Jesus Christ. Jesus Christ was the R, the very strong R, competing with Intel or whatever, no? And what happened? The Japanese appear. Oh, Banzai. So they bought R, and following our dreams, they built Fugaku, who was the #1 in the world. Fugaku is the second name for the Fuji mountain. Okay. We say, Houston, we have a problem. I mean, Europe will never have processor, because even the Chinese try to do superscalar processor, but they don't have software. The problem is not the hardware, it's the software stupid, no? It's the software stupid. You need to have, why you build a big rascacielos if you don't have people to live inside? Okay, so I went to the Vatican to pray, and then I spent many days in the chapel at night praying, and then suddenly the RISC-V appeared, no? The RISC-V appeared, It's an open hardware, okay? Because every processor in the university has a RISC proposal, but the guys from Berkeley are not more intelligent than the rest, are richer, and they have more students, and they have more capabilities. So they propose an instruction set architecture that conquer the world, and then he said, oh, let's convince the European guys to use the RISC-V to build chips, and then I will put the Mare Nostrum 6, we are now with the Mare Nostrum 5, as a target for that, okay? So when we inaugurated 2 years ago the Mare Nostrum 5, this is our president, this was the president of Catalonia. I was the only one who convinced both to meet. They were 2 years without meeting. I said, guys, here you are Peter and Pedro. Pedro. Okay, so it's a joke, okay? And then I have this sentence, who is in, okay. So I convinced the European Union, and we start from the very low level building chips with RISC-V, and now we start this project, is the largest project, okay? And what happened, that the AI is changing not the way we do things, not our life, it's changing the way we do chips. And probably I am anxious to see how my friend Mark Tremblay give us information about the real chip that he's doing in Microsoft. Okay, so now the battle is how we produce architecture, the best architecture for executing AI. Okay, so, okay, why? Because the business is very big. In this year, more or less, the value of all the chips produced in the world was 600 billion American billion, 600 by 10 to 9. But in 2030, it will be 1.3 by 10 to 12. 1.3 by 10 to 12 is the Producto Interior Bruto de España. Okay? And then the majority of the difference will be for chips devoted to the generative AI. So there is a big battle, and the building of the chips probably is the ambassador, the most important geopolitical problem in the world, technical, in spite of the war, okay? This one. Everybody is there, and Mr. Trump knows very well, and then, okay, so there are initiatives from the States. What happened is that in Spain is not here, I forgot Spain. In Spain, we are devoting a lot, 12,000 billion, but it's the only one because the companies didn't contribute to any other euro. But in the state, this is the money from the state, but the companies, every company, Microsoft, I'm sure, spend more money than the whole American country. So I decided, probably was not very correct, I decided to create two things. In this field, I decided to create a group able to go from the ideas to the tape out. Okay? So I have now around 180 people who are building chips. Our target is not to build chip, is to give ideas for the companies and to give the ideas to the companies for the companies to improve, okay? So I have this thing, and we develop some, I think I had a better, here you have a better idea. These are tape out with it, okay? These are tape out with it, and the latest one has been one with the Intel, with the technology of the 3 nanometers. And 3 nanometers, and then we are going to submit in November one to the I-18 nanometers. You know better than me. Probably it's not 1.8 nanometer, it could be 2 nanometer, 2.5, whatever. Okay, but it's the most advanced chips because they had the smaller transistor. Okay, now we are now in 2 nanometers, so we are very close to the end. Okay, so we do chips, and then what kind of chips we do? Obviously, one of them vector architecture, following the ideas we were developing during many years. scalar plus vector architecture. We have several of them. We have several VPUs, vector processing unit, okay? And then due to the, I am very happy with my government because I receive plenty of money. Plenty means plenty, more than 2 million of euros, more than 250 million of euros for processor and for, this is one project I received 50 million of euros to build chips. 50 million, 50, from the recovery funds, okay? And then we create this Barcelona, and then I convinced Pedro Sanchez and Pat Gelsinger, and they signed an agreement in Davos, but after that, I don't know if it was because the signature, that some virus attacked Intel, and you know that probably there is no medicine for this virus, no? And the agreement was to devote 20 million each during 10 years. So to create a lab in Barcelona for 400 million of euros, where Intel will contribute with 200, and the Spanish government will contribute with 200. Pat Gelsinger came to my office when mobile 2 years ago. I said, Mateo, please give me more time in order to recover it. Well, he's outside Intel. Okay, so I received from the Spanish government 2 years and a half to follow the agreement. So the contribution from Intel is that we are paying half the price of the tape out. The tape out are very expensive with this technology. Very could be 15 million of euros as a tape out. Okay, so we did this one is already working. Okay, we produced that, and by the way, in the previous processor I saw, we had several systolic array processors. We have different accelerators. They are not just superscalar or vector architecture. We had different accelerator inside the chips, okay? So we have already, this is the Barcelona Zeta Scale Lab. We have, and then this is the new one. This is the one we are going to have, we will receive the chips 4 or 5 months from now, okay? This is un pepino, no sé cómo se dice en Chile. It's very strong, 1.8, and we are going to have several vector architecture, a multi-core with vector architecture, very powerful. So this is this is the project in Europe that we are coordinating. This is one of my ideas, 240 million of euros. So, but the money is for the companies, it's not for BSC, unfortunately. We just received 15 million to coordinate and to do to have the ideas for the next generation. And this OpenChip is the company we create in Spain, an accelerator who has now around 300 people, okay? So finishing the computer architecture, I am finishing now really. So the computer architecture that TOMAS started was continued by my student. Now, unfortunately, I am devoted just bureaucracy. I create I build my own jail. Without knowing that, I don't know, no, really. Today at 3 a.m. I was with the jet lag, talking to the guys in Spain. Problems. They don't give me any good news. So you know these guys. So I mean, you had we are very active in computer architecture, as I say. There is this guy, Miquel Moreto, was after his thesis was 2 years in Berkeley. He's the guy, many PhD, many topics. Okay, this guy also. So we are very, very active in the field of, and this guy, these are first class. These guys are the guys who have 80 people belonging to the computer science devoted to the design of hard real-time hardware, which is very difficult, very, very difficult, okay? Infrastructure, methodology, okay, microarchitecture. This is the faster superscalar processor we have. Now it's an 8-way superscalar processor with a very good branch, it's very good. And we did the tape out for that. So at the superscalar, we are very okay. The responsible for the VPUs is an Italian guy. FPGA, synthesis, technical management, blah, 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 open software, okay? Here we have the chip, but now, conclusion. We are many, and we do many things, and this is the last one. I mean, without university, we don't go to any place. So, under the suggestion direction of VSC, we convinced to 33 Spanish universities to share the teaching, to share the design on RISC-V, okay? And then we are very happy. We are waiting for the money from the ministry, from Javier Ponce, your old boss. Okay. Javier Ponce is the guy who has the money. And then I think it's unique. The RISC-V allow to the university to collaborate as we do collaboration at the supercomputing level. This is very important, okay? We start this computer and I finish my talk because Jaime is Mateo. Thank you. No question, everything was very clear, no?
Thank you very much, Professor Valero, for such enriching presentation. We will now take a short coffee break.